In this video, we will introduce the first part of the fundamental theorem of calculus. Before doing so, let me remind you of some terminology. Some topics that we've discussed recently. The indefinite integral of a function, i.e. antiderivative, is a family of functions of the variable x. So as a reminder, typically we might think of this as being big F of x plus c, where f of x is any antiderivative of little f, that is to say big F prime is equal to little f, and c is any arbitrary constant. So because c can be any constant, this is an infinite family of functions. Now on the other hand, the definite integral, which we've recently introduced, is actually a number. It represents a net difference of enclosed areas. With this in mind, I'd like to ask the question, what is the geometric interpretation of the function a of x, which is defined to be the definite integral from a to x of f of t dt? So in terms of a picture, if we have the function y equals, say, f of t, and we'd like to evaluate the definite integral from a to x, well, the definite integral from a to x corresponds to the net difference of area enclosed. So a of x is equal to this enclosed area. And this function a of x, I personally think of it as being an area function because you're calculating this net difference of enclosed area. But in terms of the textbook, they will refer to this as an accumulation function. You're measuring how much has accumulated underneath the curve. And this area function or accumulation function is exactly what is discussed in the first part of the fundamental theorem of calculus. So the first part of the fundamental theorem of calculus essentially tells us that if we differentiate this area function we had on the previous slide, what we get back is the function value f of x. And note that what we're dealing with here, this definite integral from a to x of f of t dt, was what we called a of x, so it's most definitely a function of x, so we can differentiate it. And when we differentiate it, it almost works out too good to be true. We just take this x, which is the upper limit, and we replace each t in our function by that x. Now, just to give you an idea, what's the geometric interpretation of this? So a of x, the thing that we are differentiating, is this enclosed area. And we would like to know the derivative of it, which is a fancy way of saying what's the rate of change. That is, as we change x a little bit, how does that affect the accumulated area? Well, if you think about changing x a little bit, how is that accumulated area affected? Well, essentially, you're adding a little bit of area, and that little bit of area you're adding has height given by f of x. So you see that the function value at x is really giving you the rate of change of how much area is enclosed. So kind of a geometric interpretation. So put in words for you, the rate of change of the enclosed area is the value, i.e. the height we had in that previous slide, of the function enclosing the area. So let's look at a few very typical examples. Let's find the derivative of the given function. So let me recall from the previous slide, we had the formula that the derivative of the definite integral from a to x of f of t dt is equal to f of x. So essentially what we need to do is note that we're going from a number as our lower limit of integration, and then the variable x, we just plug it in for t in our function. So in this function, we have f of t is the square root of 1 plus t squared. We're integrating from a number to x, so 0 is playing the role of a. So we simply take that x and we plug it in for t. That is to say g prime of x is the square root of 1 plus x squared. it almost seems too good to be true, in the sense that no real work is required besides recalling what this first part of the fundamental theorem of calculus tells us. Now the second example is going to require a small bit of extra work. This function doesn't have the desired form. We need to go from a number to the variable x. Here we're going from x to a number. So in order to get this in the desired form, that would be 1 to x, we have to introduce a minus sign. So recall and here we're using a property of the definite integral, and that property of the definite integral is that if you have the definite integral from a to b of a function f of x dx, and you change around the limits of integration, that is to say you go from b to a instead, what that's going to do is introduce an extra negative sign. So here we've flipped around the limits of integration, which introduces an extra negative sign, and it puts it in the exact form that we would like. We now take this x when we differentiate it and we just plug it in for t. So g prime of x equals minus the cosine of the square root of x. All right, so now let's look at an example that's going to require, once again, just a bit more work. So the basic form is there. Our function goes from a number now to a function of x, and then we have f of t dt. So instead of directly applying the first part of the fundamental theorem of calculus, I'm going to note that we can really think of this function big G as being a composition. So let me just note that if I define little g of x to be the definite integral from 1 to x of secant of t, we see how this function is defined. Whatever we plug in for x needs to become our upper limit of integration. So in this case, big G of x, the thing that we would like to work with, is g of x to the fourth. That would be the integral from 1 to x to the fourth, secant of t dt. So by the chain rule is what we use to differentiate a composition. We'll have g prime of x is going to be, well, the derivative of the outside evaluated at the inside multiplied by the derivative of the inside, 4x cubed. And let's just note, what is little g prime of x? Well, by the first part of the fundamental theorem of calculus, little g prime of x, well, we just take that x and we plug it in for t. So that would be secant of x. We wanted to know g prime of x to the fourth. So instead of plugging in an x, so whatever goes in the box for x on the left goes in the box for x on the right. So this would be secant of x to the fourth times 4x cubed. And that is the desired derivative. And this can be generalized very nicely. All we've done here is apply the chain rule. So let me summarize. So by the chain rule, if we would like to differentiate, say, from a number a to a function of x, on the previous slide it was x to the fourth, f of t dt, what we need to do is take this u of x, plug it in for t. That's how we get the f of u of x. And then by the chain rule, we multiply by u prime of x. So it's a very nice pattern. So one more example. So the square root of sine t is going to play the role of f of t, and the x squared plus x is going to play the role of u of x. And what we do is we take that u of x and we plug it in to sine of t. So g prime of x is going to be the square root of the sine, and the t becomes our u of x function. X squared plus x. And this would correspond to the first part of the product that we have above. And then what we need to do is multiply by the derivative of u of x, where this second part, the derivative, is corresponding to the u prime of x. So now just to evaluate that derivative, it would be the square root of the sine of x squared plus x multiplied by 2x plus 1.